right? That it didn't cross 0?
Yeah, yeah, you know what, and I said the turnovers per game after, and I said the same thing, that it
Okay,
didn't cross 0.
that it didn't cross 0, okay.
But we'll just look at them individually right now. So, but I still wanna know how you're gonna come down on this hypothesis test.
So which p-value would you use, the intercept, or would you use
That's
the?
the turnover.
You
That's
use
the threshold.
P
the
value.
field goal percentage,
Field
right?
goal, so that's 0 point.
That's the one I would use. If I was doing a hypothesis test on a field goal percentage, I would use the p-value for field goal
So I
percentage.
would fail to reject because, with the p-value, because it's above the .05 significance level.
Oh, no, it's below.
Wait, just kidding.
Stats, sense of humor, I like it.
It's like,
So then, no, I would reject it because it's below it.
You would reject this, and this is another way of saying that there's no useful predictive value, and you would assume the alternative, which is another way of saying there is predictive value. All right, and how about for this turnovers per game? If we were to set up the same hypothesis test, if I were to put, instead of slope 1, put 2, 2, instead of an arrow this way, I do it with this one. All right, true. Again, just Monty reminded us, this is the sample slope coefficient. But let's talk about the true population slope, and let's assume it equals 0. Let's set up an alternative hypothesis that does not equal 0. Where do we come down on this test? Draw a line in the sand. Which side are you standing on?
same value. What is that third variable?
Ugh.
Which one?
Yeah, what's B2?
So.
Oh, that's the turnovers, right?
Where are you looking?
I'm just looking at I'm trying to figure out which
Those
variable
are,
that
that's
is.
turnovers.
That's turnovers. we're looking
That's
at, right?
turnovers, the
Yeah, we got the slope coefficients here. Sorry, someone said they were confused. That's not true.
Okay.
Yes, Con.
So I'm assuming I'm doing this the same way as the first one, right? Okay, so my p-value is really close to that .05. So like if I round up, I'm almost at that .05, so would it?
Nah, you don't need to round up. No,
Alright,
don't
so
round
then
up.
I failed, or I reject it.
You reject. Yeah,
Well,
you reject. It's close. Like, it's so close. Like, what if your significance level was 1%? What would be your decision then? Fail to reject. It does not pass the 1%, but it does pass the 5% threshold. You would reject this, and you would assume the alternative hypothesis, and you would say both slope coefficients have a, we have there's statistical evidence that they have predictive value. All right, and how would we get that? Well, we could look straight at the p-value like Connie did. We could also set up a hypothesis test and see these t-stats. All right, how's that? That's actually just pretty much everything we did last week, except we just added a different variable. Any questions or concerns on that? All right. So these next slides just summarize, I think, everything we have talked about. This is the estimated regression equation, which you pulled off Excel. We have a way of interpreting these slope coefficients, which we did. I think I compared Anthony's team to Lisa's team. All right. Now we're going to talk about performance measures, and 3 of them are pretty much exactly the same, and then there's a 4th one, which is just kind of, we'll talk about it for a couple minutes since it's intuitive. I won't get into the math of it. Coefficient of determination, also known as the R-squared, also known as the percent of the variation that is explained by this regression equation. Sum of squares regression divided by sum of squares total, same thing. The multiple correlation coefficient, the R is still the square root of R squared. Thirdly, we have the standard error of the estimate. which is pretty much the exact same thing we had before. This is the sum of squares error. That's the equation. I actually probably should have put that up there to avoid confusion, but that's what it is. And it's the same thing last week. Remember, it was the sum of squares error divided by n minus 2 is what we did last week, and we square rooted the whole thing. Except this week it looks a little bit different. There's this n minus k minus 1. K is the number of independent variables. So suppose you have one independent variable, like time spent online. K would be 1, so you'd have n minus 1 minus 1, also known as n minus 2, which is exactly what you did last week. You used this equation last week without knowing you were using it. Now, if we have two independent variables, we take n minus 2 minus 1, so n minus 3. If we have 6 independent variables, we take n minus 6 minus 1, n minus 7 is our degrees of freedom. We'll have more and more unknowns, so we'll need to account for that when we look at the t-distribution. All right, good there. This last performance measure, the only new one for tonight, is called the adjusted R-squared. What the adjusted R-squared does is it penalizes a regression equation for adding more independent variables. Now you may recall, I mentioned at the beginning, that as you add more independent variables, you keep throwing more and more things into your regression equation, that the R-squared will always increase. It's impossible for it to decrease. It can either stay the same or it will increase. But suppose you just keep adding more and more things because they give you 1% more of explained variables, and you have 20 independent variables. That's a lot of work. That's not as good of a regression equation as someone else who has a regression equation with, say, two independent variables that explains almost as much of the data. So adjusted R-squared just penalizes as you add more and more independent variables. Adjusted R-squared gets lower. And that's all you need to know about adjusted R-squared. When somebody comes up to you and says, my R-squared was 97%, you can say, well, what was your adjusted R-squared? And they'll be like, yeah. All right. Okay, so we're ready for the big new thing tonight, which is that F-stat, which allows us to look at the regression equation as a whole. So the individual t-stats, that's what we use to do a hypothesis test for each individual coefficient. You can see we did a hypothesis test for this one, and we did a hypothesis test for that one using the t-distribution. F-distribution is something that just allows us to more easily look at the whole regression equation. So we can compare both, in this case, independent variables, and we can say, is there something of value in this whole regression equation? And the F-test will tell us that. And if the answer is yes, then we will proceed and we will do t-tests for the individual variables. Now how the F-test works, the F-stat, it is roughly explained variation over unexplained variation. And we want a lot of explained variation, and we want a very small amount of unexplained variation. So if we have 10 times as much explained variation as unexplained variation, our F-stat would be 10. So it's 10 divided by 1 would be 10. So the higher the F-stat, the more our equation overall explains. And I say roughly because I just need to show you a couple little changes you're going to make before you do the calculation. But just intuitively, it's explained variation over unexplained variation. And we'll look at a distribution. We'll look at a frequency distribution, the F-distribution, which will tell us how likely it is to have an F-stat of, say, 10, assuming that there is no useful predictive ability in this equation. And how we'll do that, I'll actually write this over here. We will often do a null hypothesis test for the whole regression equation, and we will say the null hypothesis is all the slope coefficients equal 0. Every single one of them. So v1 equals v2, and they both equal 0. That's our null hypothesis. Also, another way of saying that, there's nothing useful in this whole regression equation. I don't care that you did 2 variables. Alternatively, one of the slope coefficients is not equal to 0. One of the b's is not 0. Okay? So we will look at something called this F distribution, and we will say, given this assumption, is the sample data highly unusual? If it is, we will reject this assumption, and we will assume this is true. So let's assume the null hypothesis, everything is equal to 0, no predictive value anywhere. Then let's look at the sample data. Explained variation over unexplained variation. Well, if it's 10, we might consider that highly unusual given this assumption, and we would reject this and assume the alternative that one or more of the slope coefficients is useful and not equal to 0. And how this F distribution works is it says, well, if the unexplained and the explained were from the same population, there's no difference between these two, then we would expect the F-stat to equal 1. So if this null is true, nothing useful anywhere, we have not found any way to differentiate the explained and explained and unexplained variation, they're just the same thing, then we would expect the F-stat to equal 1. And how your textbook explains that, how the F-stat more specifically does that, is they say if we were to take a sample from a certain population, population Q, measure the variation in it, and then we were to take a sample from the sample from the same population Q, measure the variation in it, we would expect them to be the same, because they came from the same population. And we would expect this F-stat to be 1. Now there's always a chance we could grab a little bit of a weird sample from population Q the first time, grab a weird sample from population Q the second time, and this could be different than 1. There's always a chance that that could happen randomly, and this is still true. But as it gets higher and higher and higher, we say that's more and more unusual, and let's reject that null hypothesis. So, assuming the explained and unexplained come from the same population, we would say the F-stat would be likely to be 1. And this F distribution looks like this. The peak is 1. So, again, under this assumption, nothing useful anywhere in this regression equation. And I know it's like weird because we're trying to think of how we could prove that that's not the case. But under the assumption, nothing useful anywhere, slope coefficients are 0, the explained variation and unexplained variation are completely the same, then we would expect explained over unexplained to be 1 most of the time. Or not most of the time, most commonly. It might be a little bit more than 1, might be a little bit less than 1. But as it gets further and further above 1, what that means is this explained variation is significantly higher than the unexplained variation in the whole model. And we get to a point we'll call our F critical value, where we say that is so unusual, given this assumption, that we would rather reject this assumption and assume the alternative that we have something useful. Okay. Everybody take a breath. How you feeling on that?
It's a good concept.
So it all comes, there's three components here. There's this graph, we're concentrating explained over unexplained. There's, keep in mind, this is what we're trying to test. And if this is true, we would expect the f-stat to be 1. If it's something other than 1, all right, it might be a little bit, it might be fine if it's a little bit higher than 1, but the further and further it gets away from 1, the more unlikely it is that this is true.
Okay, can you say it one more time?
So we would expect, all right, so we're trying to compare unexplained, explained variation to unexplained variation. All right, and we, actually let's do this, Monty. Let me show you how to read the F distribution really quickly. And then let's take a break after that. No, actually I changed my mind. All right, I'm going to explain this one more time and then we'll stay here for a few minutes. So where should I start?
Whichever way.
Start from that slide.
Start from this slide. All right, so f-stat compares explained over unexplained in the whole model. And that's different from the t-stat we use for individual coefficients.
So what does this, so the F distribution is the explained variation statistically different from the unexplained variation?
Yeah, in the
Okay,
whole model.
So what does that mean? Like I would say in layman's terms, but because, we're supposed to be learning this in that way, so.
Yeah, well, yeah, sure, in layman terms, if this is very much different than this, then that means you've created a line of best fit, a plane of best fit that significantly separates the explained from the unexplained. So, yeah, that's good, right? That's what we're trying to do. We're trying to explain as much as possible and leave as little as possible unexplained. So if we're able to do that, then this f-stat would be high. If we were not able to do that in any way, shape, or form, this f-stat would be 1. So this null hypothesis, it assumes we haven't done anything to differentiate explained and unexplained. And the f-stat would be 1. So if we have done something to differentiate it, it's going to be higher than 1. And the question is, how much higher does it have to be than 1 before we say, all right, right on, you've created a significant model? Does it have to be 5? Does it have to be 6? Does it have to be 10? Well, we're just going to look in the back of the book. I'll show you how to read the F2. It's easy. With me? So, okay. I could go either way on the break now. If you're feeling like overwhelmed, we should take a break. If not, I'll show you a couple calculations and then we could let it sink in.
We should take a break.
Let's take a break now. So, there are things that we need to adjust to this. It's not just explained over unexplained. It's just a couple little silly things that we need to do. All right. So this is what we said, the null hypothesis that everything equals 0. Alternative hypothesis is that one or both of the slope coefficients is not equal to 0. We have a print out, just as we had before. We could look at it if we wanted to analyze it. We will not. We'll save that. But we will look at this F statistic, and we will look at the things that produce this F statistic. Now remember I said that this, the f-stat was explained over unexplained, and look at it, it's 9.5. What do you think about that?
That's good.
Yeah, that's a lot of explained to unexplained ratio. Fantastic. Now I'll go ahead and jump the gun here and have you look at this f, this significance f. This is the p-value for this f statistic for this hypothesis test. So looking at that p-value for this f statistic for that hypothesis test, what do you conclude?
Would I be reading it the same exact way? Okay, so then I would reject, at a 5% confidence, I would reject it because it's below 5%.
You reject what?
I,
What are you rejecting?
the,
Which one?
The first hypothesis
Yes, the first hypothesis, which says what?
said none of them are.
None of them are significant. Alright, so you have overwhelming evidence that this is true. That at least one of them is significant. You got a crazy high F statistic, a crazy low p-value for your F statistic. And in fact, Connie, you said that you would reject it at the 5% significance level, but in fact, you would reject it at an even lower significance level than that.
Why?
Well, this is 0.001, that's 1/10 of 1%. You would reject it at the 1% level. You would reject it at the 0.5% level. So, crazy significance. Alright, so that's that. Now in terms of how we calculate this 9.5. Alright, so it's not just explained over unexplained. It's not just that. We need to adjust this explained and adjust this unexplained. How we adjust the explained is we take the sum of squares regression, the explained variation, and we divide by the number of independent variables. So the more independent variables we have, the more explained variation we would expect there to be. So we take explained variation divided by number of independent variables. And in this case, number of independent variables is 2. So 2664 divided by 2 gives us 1332.
And that's the MSR?
Yep, that is also known as the mean square regression.
Okay.
So that is explained variation per independent variable. Okay.
Oh, so the mean square.
Yep.
Okay, that would be the MS.
Yep.
Okay.
Mean square. It says MS because it applies to both of these, but this is mean square regression and this is mean square error.
Okay.
Alright, so that's what we do for the top, the explained part. What we do for the unexplained part is this is our total unexplained variation, 2375. And we essentially divide that by the number of sample points, the amount in our sample size. And remember we had 20 teams, 20 sample points, and we get that to amount of unexplained variation per sample point. The more samples we have, the more unexplained variation we would have, so we don't want to penalize just because we used a large sample size, so we divide this by the sample size. But it's not quite the sample size. I just want to make sure you're intuitively with me that we divide by the sample size. Alright, and we get approximately unexplained variation per sample point. We don't divide exactly by the sample size, we divide by sample size minus k minus 1.
No, that's right.
K is 20 though?
K is 2, k is number of independent variables.
2.
Okay, yeah, we have 2 independent variables.
Okay.
Oh.
So the more independent variables we have, the more unknowns we have, so this would make this number bigger.
So Professor, you're saying this 20 minus 3?
Yep.
Is that what it
Yep.
is?
Yep.
What about the number above? Why is it 2 then?
This, to get the explained, get the the top part of the F-stat is our explained variation. It's not quite explained variation, it's explained variation per independent variable. So explained variation divided by 2, we could say explained variation divided by k, and k is number of independent variables.
Okay.
So explained variation divided by 2 gives us this, and this is roughly thought of unexplained variation divided by sample size, but we adjust sample size slightly, sample size minus k minus 1. So 20 minus 2 minus 1 gives us 17. And 2375 divided by 17, I can do that in my head too, it's 139.7. Just kidding, it's a joke, I can't do it in my head. And then we take 1332 divided by 139.7 and we get 9.5.
What, you did the 1332 divided by 139?
Exactly.
Okay, and that gives you the F stat.
Yep, exactly.
And then the F significance is the p-value of F, and that tells you how likely, or the, whether or not to fail or,
It tells you both. It tells you whether or not to fail or reject, but I like the way you started the first time. It tells you how likely this F statistic would be if this were true. If there were truly no
oh, okay.
predictive value anyway, the chances of us randomly getting a 9.5 F stat, 1/10 of 1%. It's possible, but very unlikely, so I would rather reject the null and assume the alternative. We've got something useful here.
So the more unknown variables, I'm still not connecting that. You said the.
Yeah, so K is number of independent variables.
Right.
And I just threw in there, and it's not critically you understand that, but the more unknown variables we have, the t-stat, the t-distribution gives us a wider interval to work with
Okay.
to account for those unknown factors. Okay. So you've got f-stat, right? So the f-stat allows us to look at the whole regression equation, the combination of these two, and we say, is there something valuable here anywhere? If the answer to that is yes, then we proceed and do the t-stats, the confidence intervals, same stuff we did last week, all that stuff with simple regression. Any questions at all? Alright, these next slides just sum up. This mean square regression, this is explained variation divided by number of independent variables. So explained variation is SSR divided by independent variables K, gives us what we'll call the mean square regression. Is that column with the MS regression, MSE, mean square regression. Mean square error is the sum of squares error divided by n minus k minus 1. You take the mean square regression over the mean square error and you get our F stat. And we used the p-value version and we rejected the null hypothesis because our p-value was crazy low. It was lower than our typical 5% significance level, and it even would have been lower than our 1% significance level.
So the SSC is unexplained variation, sorry.
Yes.
Okay, thank you.
Got it. No problem.
Because
Yes?
in the Excel printout, where does it say what the confidence level is, what it is?
For the F stat or for these?
When you said that using the p-value reject,
Yep.
p-value greater or less than.
Oh, so this is the p-value for the F stat. But again, it's the same question I think you asked last time. We choose the significance level.
Is it based on the printout 5%? Or
No,
you just picked?
no, this is it's the same thing as last time. Excel just randomly inputs 95%, which would be a 5% significance level. But if your standard is higher than that, if you want 99% and a 1% significance level, then you just have to read this. And this is, and this might even be more of a reality of how p-values are used. You're not going to walk into your manager's office and say, I rejected the null hypothesis. You're going to say, all right, I decided that I had overwhelming evidence to conclude this because 1%, less than 1/10 of 1%, the chances of this happening randomly are this. You would probably explain this p-value, would be the way you would go. All right. I think these, okay. Let's, so we knew we could reject the null hypothesis of this with our p-value. We could have also used the critical value approach. We could have also drawn a normal it's actually not a normal distribution. It's different than a normal distribution. It has a long tail centered around 1. All right, this is F distribution. And we said if we get a crazy high F-stat, like 9.5, then we're going to reject the null hypothesis. The question is, what is this critical value? What is this number? So we need to look on the F table, all right, and we're going to have k degrees of freedom in the numerator and n minus k minus 1 degrees of freedom in the denominator. So if you turn to the back of your book in the F-stat, you will see that you can choose numerator degrees of freedom and denominator degrees of freedom. Sounds intimidating, but it's not that difficult because before you even start to look, you will choose your significance level. All right, Eric, you'll choose the significance level to start with either 5% or 1%. And I think you'll look across the top for numerator degrees of freedom. You look across, you look along the vertical axis for denominator degrees of freedom, and the one in the middle will be the critical value.
What?
Where is it? Wait, which?
So the numbers across are the critical value.
You're looking at the wrong thing. Wait a minute.
F-stat?
Never mind. Never mind. The top is the, yeah. All right, so if you're looking at, say, the 5%, the top is the degrees of freedom on the numerator. The up and down is the degrees of freedom on the denominator. Exactly, you had it right there. Denominator,
What do you
numerator.
if you have 0.5%?
So what are our degrees of freedom for this test? We had numerator degrees of freedom was this this MSR. Actually, I apologize. I didn't really explain how degrees of freedom related to this, but it's something we've already used before. The degrees of freedom for the numerator is going to be 2. It's going to be k, the same thing we divided by the explained variation. And the degrees of freedom for the denominator is going to be n minus k minus 1.
Hold on. Is that in the pamphlet?
Yeah, it's in this slide right here. So F distribution with k degrees of freedom in the numerator and n minus 1 minus k degrees of freedom in the denominator. Yes, Rob?
So the degrees of freedom is always the number of independent variables to them, right?
Say again?
The degrees of freedom is always the number of independent variables as well.
Oh, yeah, in the numerator.
Yes.
Yeah, the number, yes, it's k, which is the number of independent variables. That is your numerator degrees of freedom.
Yeah.
That is this numerator degrees of freedom. So, all right, when you turn to the back of your book, say you choose 5%, you're going to look across the top for 2 degrees of freedom, and across down the side for 17 degrees of freedom. What's the number where those meet?
3.596.
Yeah.
3.592.
Yes.
Okay.
So first, top.
And then you go down to 17.
Two, the top.
3 point.
So that's the first,
3.52.
That's two.
Yeah, 5
and
degrees.
17. Would be here, and that would be
So, degrees of freedom.
3.59.
Oh, okay.
As long as you have this, we can figure things out.
Yeah.
With 5%.
Okay.
Then there's another one with 1% of the visa.
Okay.
Good,
Now.
good, all right. Excellent. So now we have an F-test we can use for the whole thing. Once we do that, we go back to our original T-tests. I believe this next slide is just everything summed up. The F-stat.
Do they give us the 3.592 in there or no?
They do not, I'm guessing the next slide, one of these slides might. This, do you have a, no, I guess it'll actually be here somewhere. This next series of slides, it's just a lot of information that you've already gone over. It's the F-stat, looking at everything overall. And then it's, now let's look at the individual coefficients and do t-tests for these. And look at the standard error, do a hypothesis test for that, look at the p-value for that. It's just all that information summed up for our college sports example. All right, so this is a sort of template for the F statistic. Here is some information about the F test, which I think we've talked about fairly thoroughly. So explain, can't explain. Really large F value is good. This ratio, if that's huge, it's 9.5, you're like, that's crazy. There's definitely something valuable here. This just is more verbiage along the lines I think we've already explained. The F-test argument summed up is something if you need a little help getting to sleep at night. Tonight when you go home you can read that, but it's just the same thing that we talked about. All right, inference side of multiple regression. All right, so now let's infer and do confidence intervals. All right, let's look at our F-test results and say, do we have something significant if we were to try to relate this to the whole population? And then let's do the individual coefficients. Let's do t-test for those. And let's throw in confidence intervals, plus or minus 95% confidence for those individual coefficients. All right. So this slide, we've talked about it before. You've heard me say it 3 or 4 times, but it's just in summation. F-test determines the overall significance. It gives us a method of looking at both these variables, in fact, all 20 of them at the same time. And null hypothesis, is there something useful anywhere? T-tests is what we can do for individual significance for each individual coefficient.
Ah, finally dawned on me like,
That's
okay,
what I like to
why
hear.
are we doing that? Okay, all right.
All right, I'm glad we paused on this slide. I've thrown it in like probably too fast earlier on in class.
So t-test is for individual coefficients and
The
F-test is for the whole, the overall.
Yes, fantastic.
Because just like he said, wouldn't you do them each individual? Does that have any sort of correlation to what the t-test does?
Yeah. So you could do them individually for 2 reasons. One is to deal with that question of multicollinearity that we started class with. The second is you could do it. The F-test and the t-test are exactly the same for simple regression. In fact, let's look back here. Remember this old slide we spent all of last time and a good chunk of the first time on? Dun, dun. So this F significance, 0.1686, does that look familiar?
Yep.
Remember, it was the exact same thing as the p-value for our 1 coefficient. So this tells us the overall, the entire test, everything. And it just so happens that the entire test is just one independent variable.
Ah, okay.
That's why it's a
Gotcha.
number.
Yeah, so if we had more, this changes, and the p-values for the individual coefficients
They
still
will be
be.
listed.
Yep, exactly. Exactly.
Professor, is next week all multiple choice?
What's that?
The quiz for next week, is it all multiple choice?
I think there's a few multiple choice, but the multiple choices are actually harder because it's like
Tricky.
it just asks you. There's a couple multiple choice questions, but it's not good news in that.
And then
particular-
Blackboard changes your answer.
And then Blackboard changes the answers on. Alright. I think for the quiz, it's, you know the F stat, you just need to be able to calculate this F stat.
Can we do a couple of the problems?
Can we do some of the homework problems?
425,
Step by step.
1.8.
Alright.
So we know what we're doing, where we're going.
Let's do it, let's do some homework. Let me, should I, what do I got?
And make sure that the quiz mirrors the homework.
No idea where we're going.
Okay, can I go through the rest of the slides though first?
Yeah, let's move on.
Do homework,
Okay.
is that okay?
Yeah, sure.
I mean, if we need to, what do we do with this? I don't know, is there one, where are we now? We wanna do like a,
Different side, right?
is there a homework problem that does this?
I don't want this little term is not equal to 0.
Is that where we are? Where are we? Wait, no, that's,
Go back.
alright. We were just here, and Monty said he liked this slide. And next is F stat. Is there, what's the homework, is there a homework problem someone wants to do?
Is this chapter 12?
Yeah,
Is this chapter 12?
Chapter 12,
I
yes.
don't know.
It's chapter 12.
Oh, it
Chapter
was
12.
just saying review in the back, 425 and 4.8.
No,
I don't know, we have
We
to
still have lots to go through.
No, but this one, it was,
Because it didn't even touch the
my
homework.
bad, I was just looking at.
It's like buried in my notes here somewhere.
Oh, I have mine. It's right here. Lessons.
alright, is somebody looking at homework problems?
Here it is.
Syllabus?
Class 7.
I gotta remember,
Homework.
today's the 17th.
Homework. Class 7.
It's a lot of homework
I
there.
don't know, this doesn't, I don't know, you all need to look through, I can't.
Yeah,
Can't.
just a minute.
If you wanna do homework problems, do homework problems, you just need to tell me which ones.
Oh, all right, let's see.
All of them.
Oh, alright, well, we only have till 9:30.
You're talking about that path that we did today, or?
No, there was, there was a point raised that we should stop and do a homework problem or two before proceeding.
Well, there's lots of them.
Alright, well, look in the book though and see which ones relate to the ones you wanna do.
Which one's related to the quiz?
Here, look at this one.
Oh, chapter 12.
So,
Class
can you
7.
give us like one that you don't know which one, like kind of that you put on the quiz?
Wait, what are we doing?
I have to see, I don't have my textbook with me.
Let's do
I don't know, it's been like 2 years since I wrote that, so.
Professor, let's
Give me a vote. 30.
Let's do 32. I don't know. I make that one. I don't always just change the number.
Yeah, Professor, why don't you do 32?
32, let's do 32.
Yeah.
What page is it on?
Yeah, for the quiz, just.
And what page is
change
it
the
on?
number
What page is 32?
471.
What's
Alright,
71 there?
I would love nothing more than to do number 32.
You sound so proud.
Professor.
472.
32. See, it has a story and everything.
Alright.
Yeah.
Go backwards.
It's gonna be on the quiz.
There's a little term paper in
Yeah,
there.
right?
And this chapter is more challenging.
Instead of
right?
split up research, it's research.
Maybe 34.
Maybe 34.
Maybe 30,
We'll do
34
that
looks
one, too.
complicated. Let's do 34, yeah.
Yes, 34.
34.
Let's do 34 instead.
Yeah.
So what, did you say 472?
71.
471. 471.
Alright.
Yeah,
Is 34 now the preferred one?
Yeah, it has more complications in there.
Oh, this is a dummy variable, we haven't gotten to that yet.
Oh,
It's too far in there.
Yeah, yeah.
So we have to proceed with class to get there, is what you're saying?
For this one, I'm not opposed to doing a different one.
Where's the 34? Yeah, 34 is the last
then-
problem on the homework assignment.
Wait, we have, where are we?
So that's, so we should do it for
So we can do 28 then, or,
we're spending too much time.
you can't, to,
we could do 28. Isn't that what we're doing
You,
It's a very short chapter.
there's gonna be a hypothesis test one. I'm sure I must have put at least one hypothesis test on the homework. Where you have to use the F-stat.
You put like all these exercises here, you put 2 to 34.
Yeah, but look at the actual problem and see if it says compute the F-stat and run a hypothesis test.
Hold on.
Okay, number 10. That's a lot of homework.
30, let me see, 30, is 36 in here? I just don't know what. No. 34.
Oh boy, you can look here.
No, I don't.
Yeah, but we're doing this one.
No, I know, but I'm just looking at what we'll do next week.
Should we go to the dummy variable one? You wanna do that one? I'll teach you dummy variables and then we can,
On
As
page
long as it's in the quiz.
473, there's an F distribution on here.
Yeah, right.
you wanna do dummy variables?
Page 473.
Alright,
Alright,
let's do dummy variables and we can do number
oh,
32.
alright.
Or actually, there's a problem in the slides we can do, but we can your choice. All right, dummy variables are qualitative independent variables